So in 7.5, we're going to review inverse trig functions. So remember that our trig functions, sine, cosine, tangent, and so on, they're not one-to-one functions. So in order to even define our inverse trig functions, we have to restrict the domain of sine, cosine, tangent, secant, cosecant, and cotangent. So in this first graph, which is sine inverse, we had to restrict sine from negative pi over 2 to pi over 2. Okay? And if we do that, then we create the sine inverse function with domain negative 1 to 1 and range from negative pi over 2 to pi over 2. So our cosine function, we restricted to 0 to pi. So that becomes the range of cosine inverse with domain negative 1 to 1. Okay. Tangent inverse has domain of all real numbers, but a range of negative pi over 2 to pi over 2. And now notice that tangent inverse, remember these are arrows here? It goes on and on forever, whereas in sine inverse, cosine inverse, it doesn't. So let's go ahead and go to our cotangent inverse. So cotangent inverse has a domain like tangent inverse from negative infinity to positive infinity and range from 0 to pi. And like tangent, remember these are arrows, this goes on for and ever. Okay? And I'm going a little backwards. Our cosecant is, cosecant inverse is going to be restricted so that our x values are less than or equal to 1 or greater than or equal to 1. The range is going to be from negative pi over 2 to pi over 2, okay, as long as our where our range is not equal to 0. And then secant inverse, domain is x's that are less than or equal to negative 1 or greater than or equal to 1, same as cosecant inverse, but here the range is 0 to pi, but not equal to pi over 2. So we also have, with our trig functions, what we call the canceling property. And the canceling property says that if you put in x values from negative pi over 2 to pi over 2, and you're composing sine inverse with sine, then they cancel. And what you put in is what you get back out. Okay? So these would cancel. If you're composing cosine inverse and cosine, as long as you're putting x values 0 to pi, then what you put in is what you get back out. And these cancel. So we have these canceling properties for tangent, composed with tangent inverse, cotangent, secant, and cosecant. You just have to remember that we have restrictions on the x values that we're putting in. So as long as you're putting x values in the domain, the restricted domain of tangent, cotangent, secant, and cosecant, then you can just cancel. What you put in is what you get back out. What you put in is what you get back out, and so on. Okay? So that would be if you're composing and you're putting values into your trig functions first, and then into your inverse functions. So remember that when we compose functions, we always put values from the inside, work our way out. if you're putting in the inverse functions first, then remember we can only put in the x values that are in their corresponding domains. So if you do put in the x values in their corresponding domains, then they cancel. What you put in is what you get back out. Cancel, what you put in is what you get back out, and so on. Okay, so let's go on to our next page. And let's go ahead and in example 1, try to figure out what some of these values are. Okay? So when we put in 1/2 into sine inverse, you have to ask yourself, is 1/2 in that range between -pi/2, or between, -1 and 1, and 1/2 is. So we can use our canceling properties and just cancel, and this is just equal to 1/2. Okay, so when we compose cosecant of pi with cosecant inverse on the outside, you have to ask yourself, is pi within that range? And the answer is no. So let's just look at cosecant of pi. Remember that's 1 over sine of pi, and sine of pi is 0. So actually cosecant of pi is undefined. So this actually does not exist. You could write undefined, or remember you can use DNE for does not exist. What about if we put in 2 pi into cosine? Okay. Well, that's not within the values that we're allowed to in order for this to cancel. So cosine inverse of cosine of 2 pi is not equal to 2 pi. Okay, because 2 pi is not within our range that we're allowed to put in. So in this case, we have to evaluate these separately. We have to first figure out what cosine of 2 pi is. And in that case, it's 1, right? So then we have cosine inverse of 1. And cosine inverse of 1 is just 0. Okay. If you can't see that, remember what you can do. You can take cosine inverse of 1, let it equal to some x value, so that cosine of x is equal to 1. Now cosine is equal to 1 for 0, 2 pi, 4 pi, -2 pi. There's infinitely many values where cosine is equal to 1. But remember, you have to choose the value that's in the range of cosine inverse. So none of these will work. The only one that will work is 0. Okay, let's look at another example that comes up in trig, something nice to review. Let's say you're given cosine inverses of 3/4 is equal to theta, and you need to find sine of theta and tangent of theta. Well, the first thing you want to do is get rid of the cosine inverse because it's not helping you at all. So one thing you could do is rewrite this so that it's cosine of theta is equal to 3/4. And then we can just use right triangle properties. And here's my sad looking triangle. Oh my gosh, that's horrible. Okay, so if this were my theta angle, remember cosine is adjacent over hypotenuse, so it would be 3/4. And then completing this right triangle, the missing side would be the square root of 7. And that's it. Now all I have to do is, using that right triangle, write sine of theta equal to opposite over hypotenuse, and tangent of theta equal to opposite over adjacent. And that's it. You might have to rationalize denominators if you do end up with a square root, but ours is fine. We can stop there. So now let's do some calculus with our inverse trig functions. Now in this theorem 711, the derivative of the inverse sine is equal to 1 over the square root of 1 minus x squared. Okay. And here we're restricted to just x values from -1 to 1, and we can't include the -1 or the 1 because that will give make our denominators undefined. So in example 3a, we want to find the derivative of sine inverse of x squared. We do have to be careful because this is not just x, this is x squared. So we're going to have to use the chain. So when we do use the chain rule, okay, we're going to take the derivative of sine inverse, but remember, instead of having an x, we have an x squared. So this derivative is going to equal 1 over the square root of 1 minus x squared squared. And then because it's the chain rule, we have to take the derivative with respect to x of x squared. Okay? And that's just going to be 2x. So cleaning this up, I'm going to have 2x over the square root of 1 minus x to the 4th. Okay? And this is where we can stop. So let's try another one. Again, this involves the chain rule because we have a composition of two functions of x. So when we take the derivative, chain rule, it's always outside and then inside. So when I take the derivative of cosine, that's just going to give me negative sine. Argument stays the same, times the derivative of our argument, which is sine inverse of x. So something very nice is going to happen. When we compose sine with sine inverse, it's just going to cancel. And the reason why is because in the beginning, sine inverse of x is only defined when x is in -1 to 1. Okay? So we can assume that those are the x values that we're using and we can cancel them. So this is just going to be negative x times 1 over the square root of 1 minus x squared. And again, cleaning this up a bit, that will be x over the square root of 1 minus x squared, and I'm going to take its negative. So this would be our derivative. I apologize. Okay, let's go on to the next page. Sorry, I had a little bit of pen all over the place. Okay. So on the next page, we're going to be looking at the derivatives of all of our trig functions. Now, I just wanted to let you know that you do not have to memorize these. Theorem 7.12, this would be given on the exam. Okay, you do not have to remember these. That's just ridiculous. You just need to know how to use them. So in example 5a, if I'm taking the derivative of tangent inverse of x squared plus 1, again, I'm using the chain rule. The first thing I want to do is take the derivative of tangent inverse. And the derivative of tangent inverse is 1 over 1 plus the argument squared. Okay? times the derivative of the argument. Okay, so again, I'm using the chain rule. So the derivative of x squared plus 1 is just 2x. And this becomes 2x over, and now typically I would say you can just stop there, but in the denominator, I'm going to multiply this out because I will be able to combine some like terms, so it will simplify a little bit. So this is going to be x to the 4th plus 2x squared plus 1. Okay, and the reason why I did multiply this out is because I can see the plus 1 will simplify. So this is just going to be 2x over x to the 4th plus 2x squared plus 2. And now that doesn't factor, so this is where I would stop. So as just a reminder, instead of the inverse notation, you may also see arctan. Okay? And remember, arctan, arc cosine, arc sine, that's exactly the same thing as inverse. Okay? So if I was going to take the derivative of the square root of the inverse of tangent, sometimes it's helpful with square roots, although it's not necessary. Sometimes it's helpful to write it as arc tangent of x to the 1/2 power. But it's not necessary. And then that would be equal to 1/2 from the power rule, stays the same, to the negative 1/2 times the derivative of arctan. Okay. Okay. So the derivative of tangent inverse is equal to, and here I'm going to clean this first piece up a bit, 2 times the square root of arctangent. Okay, and the derivative here would be 1 over 1 plus x squared. And it's not necessary for you to distribute across the 1 and the x squared, but you should write this as one fraction. Okay? And I prefer to have in parentheses 1 plus x squared in the front of my square root. But again, that's just personal preference. Okay, never make my lines long enough. And that's where we can stop. So this would be our solution. And the reason why I didn't multiply and distribute the 1 plus x squared is it's really not going to simplify anything. So let's look at integration. In Theorem 713, we're looking at integrals of this type. Okay, if you have the integral of 1 over the square root of some number squared minus x squared, that's just going to equal to sine inverse of x over that number a. Okay, and then 1 over some number a squared plus x squared, that would be our tangent inverse. Okay? So it's 1 over a tangent inverse of x over a. And then we have a representation for secant inverse, but we do have to be careful that we leave absolute values around the argument of secant inverse. Okay. Again, Theorem 7.13, like 712, will be given on the exam. You do not have to memorize these integrals. Okay, so let's go to the next page, and let's go ahead and evaluate these integrals. Okay, so when we evaluate these integrals, the thing is we have to make it look exactly the same as the integrand. Okay, So this first one, example 6a, it's fine. One thing I could see right away is I could take out the 6. And notice in my integrand, 4 is 2 squared minus x squared. Okay. So I can see that the a that I'm using is 2. And then I just plug it in. This is going to be equal to 6 times, this would be sine inverse of x over 2. And since it's an indefinite integral, I have to remember my constant. Okay, and I'm done. The problem with example B is that it's not quite in the form that I need for tangent inverse. And since it's a plus, I'm going to try to match it up to the tangent inverse. What you first want to notice is that the x squared does not have a coefficient of 1. It has a coefficient of 25, which is not the form. Right tangent inverse, it's a squared plus x squared, where x squared is a coefficient of 1. So the first thing I'm going to do is I'm going to factor out that 25 so I can get this in the form that I need. Now, if you would also like, you could do a u substitution of 5x, but I'm not going to do that. I'm just going to factor out 25. What's left over will be x squared plus 1 over 25, okay, dx. And then I can pull that 1 over 25 out from inside my integral. And this becomes 1 over x squared plus, notice that this is 1 over 5 squared. And that's going to be my a. My a in the formula is 1 over 5. And this takes the form of tangent inverse. So this integral is equal to 1 over 25 times, now it's going to be 1 over a. Since a is 1/5, 1 over 1/5 is 5 times tangent inverse, and the argument is x over a. X over 1/5 is actually 5x plus my constant c. So on the outside, the 1 over 25 times 5, I can simplify that to 1/5. And it's tangent inverse of 5x plus my constant c. Okay, so the challenge will be to get it to look like the form in the integrand so that you can integrate. Okay, notice that I could have also done a u substitution. I could have let u equal 5x. Okay, so my du dx is just equal to 5. Or in other words, du over 5 is equal to dx. So my integral is going to be equal to the integral of 1 over u squared plus 1, and the dx is du over 5. And then I could pull the 1/5 out. I have the integral of 1 over u squared plus 1 du, and that takes the form of tangent inverse. So this is going to be 1/5, and then my a in this case is 1, so times tangent inverse of u, okay, plus my constant c. And then I would just substitute in my u value. Okay, I started with x, I have to end with x, which was 5x. So if you would prefer to do a u substitution to get it into the form that you need, that's fine as well. It doesn't matter to me which method you use. Okay. I tend to just do the math and not the substitution. All right. So let's go on the next page and let's try another example. Okay. Again, for example C, this is not in the form that I need it to be in. So I am going to, again, you could do a U substitution. And the problem is, as the previous one, the coefficient on the x squared is not 1, it's 16. So again, you could do a U substitution. You could let U be 4x. Yeah. Not going to do that. What I'm going to do is I'm just going to factor out the 16. So this is going to be underneath the square root 16 x squared minus 25 over 16. And again, I never make my bars long enough. So notice the square root of 16 is just 4. Coincidentally, that's going to cancel with the 4 on the top. So I'm going to have the integral of 1 over x square root of x squared minus 25 over 16 would be 5 over 4 squared. Okay. So now it's in the proper form where a is equal to 5/4. Okay. And this takes the form of secant inverse. So it's equal to 1 over a, which would be 4/5, secant inverse of, the argument is in absolute values. So remember, it's x over a. X over 5/4 would be 4x over 5. Okay. Plus my constant c. And I'm done. So again, you could have done a U substitution, but I decided not to. So let's look at our last example. Our last example is a definite integral. And it kind of looks like tangent inverse, but again, I have an issue here with the coefficient on the x squared. So I'm just going to factor out a 16. Or you could do your U substitution. If I factor out a 16, it's x squared plus 1 over 16 in parentheses, dx. And here you could pull out the 1 over 16 if you wish, or you could leave it in. If you do a U substitution and let it be equal to 4x, remember that you have to change your limits of integration or leave them off until the end when you substitute back in for U. Okay. So 1 over x squared plus 1/4 squared means my a is equal to 1/4. And this is tangent inverse, so this is 1 over 16. It's going to be, since my a is 1/4, it becomes 4 tangent inverse of 4x. And I'm evaluating this from upper limit 0, lower limit 1/4. So hopefully you could see that the 4 over 16 just becomes 1/4. So this is 1/4 tangent inverse of 0 minus tangent inverse of 1. And tangent inverse of 0 is 0 minus tangent inverse of 1. So tangent is equal to 1 at pi over 4, right? So this should be pi over 4. So my 0 is gone, and this simplifies to negative pi over 16. Okay, and I am done.